All right, so now we want to talk more about what it means when an object speeds up or slows down. We've talked about this before, objects speeding up and slowing down, and we've drawn sketches of the motion. Well, there's a word for this, and we call it acceleration. Acceleration is the word in physics that we use for when objects are speeding up or slowing down. You don't have deceleration, which is used in everyday language. You just have acceleration. So we've seen accelerated motion before. Think about the video analysis lab part 2, where you had objects that were speeding up and you had objects that were slowing down. So in this first example with a tennis ball rolling down a binder ramp, what you see is that the dots, the spacing between the dots gets further and further apart as the tennis ball rolled down the ramp. Because the spacing is getting further and further apart, that means that this object's speed is increasing as it moves downhill. The acceleration in this example is, so it means that the object is accelerating since the speed is changing. The acceleration here is in the same direction as the motion because it is helping the object get faster and faster. In this second example, you don't see the tennis ball anymore with the screenshot that I have here, but the tennis ball was moving, in this other student's example, was moving up the ramp. And if you look at the spacing of the dots, you see that the spacing starts big, but then the spacing gets smaller and smaller and smaller as the object moves up the hill until those dots start to be almost on top of each other. So in this example, the object's speed is decreasing as it moves uphill. What this means is that acceleration is moving in the opposite direction of motion. The acceleration is hindering the object's motion. It's slowing it down. It's like a track athlete or a football player that's running with a parachute. They might be running to the left, but the parachute is trying to pull them to the right, meaning that their motion, their velocity, and their acceleration would be in opposite directions. You'll have a chance to practice this more with another activity. Okay? But for now, remember that if you're speeding up or slowing down, you have acceleration. All right, so we're going to work this example here. We have a position time graph where it's a curve. That curve tells us that, hey, the slope is changing, which means the speed is changing. So let's calculate the average velocity in the first second, and let's calculate the average velocity in the last second. And because it's hard to read the values on the graph here, I've given a data table, and you can see the yellow and the pink sections. And the formula is right here. Average velocity is the displacement over the change in time. So to find this average velocity, I'm going to say that it's equal to, for the yellow segment, 10 meters minus 0 meters divided by 1 second minus 0 seconds, which is equal to 10 meters divided by 1 second, which is, written more simply, 10 meters per second. And that is a positive value because velocity needs to have direction. Okay, so an average velocity of 10 meters per second. I can't do the highlighting feature, but that is the answer. When we come to this next example, what we see is in the pink section is the average velocity equals 210 meters minus 150 meters divided by 6 seconds minus 5 seconds. Simplify that. That is equal to 60 meters divided by 1 second. Simplified even further, that is 60 meters per second. So that's how we find the average velocity. So note here, at the beginning, early on, so this object maybe started at rest, no slope, and in the first second it had an average velocity of 10 meters per second. In the last second it had an average velocity of positive 60 meters per second. So the velocity is increasing. Well, this is kind of like think about stairs. In the first, let me try that again. In the first second, your stairs like that. In the second your stairs like that. The third second, like that. The fourth second, like that. And so on. And what you notice is that the stairs, the height of the stairs gets bigger and bigger and bigger. That would be a challenging set of stairs to climb, and eventually you might not be able to climb it. So that is acceleration. The slope here is increasing, so the average velocity is increasing. All right, so everything in that previous slide represented accelerated motion. Some things I want to erase there. And so you note that, hey, if I found this slope at all these different points along the way, I would find the increasing velocity along the way, and I would get values that show an increasing velocity. And so our velocity time graph is positive diagonal. The velocity, which is the y-axis, is increasing as time goes on. We see with our motion map that the vector is getting bigger and bigger, showing that it's getting faster and faster, and we also see that represented with our data table. So we come here now, and what we see is we want to take these notes. We say, okay, if anything that's speeding up or slowing down, it's acceleration. We represent that with the letter A. It's a simple symbol. We figured out before how to calculate average velocity as a change in position over change in time. Now what we are looking at is the average acceleration as being the change in velocity over change in time. So just like the slope of a position time graph gives you velocity, the slope of a velocity time graph gives us acceleration. So let's look at some examples here. These are non-graph examples. We want to find the average acceleration. All right, so A equals, in this first example, you're going from 3 to 12 meters per second. So 12 minus 3 divided by the change in time, which is 3 seconds minus 0 seconds. Simplifying that, that's 9 meters per second divided by 3 seconds. Simplifying that further, it's 3 meters per second per second. We'll come back to that unit in a second. For the second one, the acceleration is 20 meters per second minus 4 divided by 2 seconds minus 0. Simplifying it, and simplifying it further, 8 meters per second per second. Both of those values are positive. It's acceleration. It's like velocity. It's important to indicate direction. Okay. So if we look at those units, so let's make up this number here. If we had positive 5 meters per second squared, and write this down in your notes, that could also be written as positive 5 meters per second over 1 second. That could also be written as positive 5 meters per second per second. Write all of those variations down. This means that for every 1 second, the speed changes by 5 meters per second in the positive direction. Okay, So for every 1 second, you see the bottom of this, the speed changes by 5 meters per second. So if you started at rest, after 1 second, you're going 5 meters per second. After 2 seconds, you're going 10 meters per second. And after 3 seconds, you're going 15 meters per second. Okay, that is what acceleration means, and that is how we represent it in words. That's how we represent it in numbers with units, and that's how we represent it as a data table. So now, whereas before we worked with a position time graph, here we're working with a velocity time graph, and we want to find the average acceleration graphically, whereas in the last slide, or 2 slides ago, we found the average acceleration from a pictorial representation. So let's find it graphically. So for for the yellow part, my acceleration is, first of all, I could say that it's 0 meters per second because there's no slope. No slope means no velocity. But if I wanted to write that out and prove it to myself, I'd say that, hey, there's a no rise divided by a run of 2 seconds minus 0 seconds. So that's the same answer. Okay. When I get to the pink section, I say, oh, decrease my font. I say, hey, the acceleration is 0 meters per second minus a minus 4 meters per second divided by 4 seconds minus 2 seconds. Okay, 0 meters per second is my final velocity. Negative 4 meters per second is my initial velocity. So negative times a negative is a positive. So that gives me acceleration of 4 meters per second divided by 2 seconds. That gives me an acceleration of 2 meters per second, and that's positive. Okay. If I go to my last segment, my acceleration is going to be 8 minus 0 divided by 8 minus 4. And that will equal positive 2 meters per second. You can check the numbers out, pay attention to the scale, note that the scale goes by 1s on the time axis and it goes by 2s on the velocity axis. And so what you notice is that the pink segment and the blue segment have the same slope, so they have the same acceleration. This line, this function, the slope is not changing. Even though the pink is in the 4th quadrant, mathematically the blue is in the 1st quadrant, there's still the same function. It has the same slope. It's a positive diagonal line, sloped line, so it has the same average acceleration. That's it. That is an introduction, or a more detailed introduction to acceleration when objects are speeding up or slowing down. If you have questions on any of this, I encourage you to go back to the parts of the video where you have some questions and check out the information.